Hello, my name is Dan Gant, and I'm going to present to you a game from the 2019 AIIDE StarCraft AI Tournament. We're going to watch the 2019 champion AI, Locutus, written by Bruce Nielsen, competing against my own bot, the second place runner-up, PurpleWave. While we watch this game, I'll discuss how StarCraft AI games work, the challenges involved, and some of the approaches these bots use to overcome those challenges. And as this match unfolds, I encourage you to picture how you might go about building your own agent for playing StarCraft or multi-agent games like it. Anyone can write StarCraft bots and compete. All of the bots in the AIIDE tournament are open source, and many have permissive licenses allowing you to use them as starting points for your own creations. There is also a large community of developers on GitHub, Discord, and Facebook who can answer your questions and point you in the right direction. Visit github.com/bwapi/bwapi and see the links for joining Discord and Facebook. This cast will be posted online after the live presentation, and if you're watching on YouTube, those links should be below. Now, to introduce these bots. Locutus, written by Bruce Nielsen, is a champion of this tournament and the 2018 CIG tournament. It's written in C++ and is based on another bot, Steamhammer, by Jay Scott, which is itself based on the University of Alberta bot by Dave Churchill. There are a lot of open source StarCraft AI libraries you can use to aid your development, and Locutus uses a few of them, including the Brood War Easy Map Library by Igor Dmitrievich, the Brood War Easy Building Library by Christian McRave, and the Fast Approximation Library by Hans Bredberg. Altogether demonstrates 10 years of progress in building agents to play StarCraft. Bruce himself has spent 2 years making Locutus to a very strong competitor. PurpleWave, which I wrote, won the 2018 AIST tournament and the 2019 SSCA to AIT and COG tournaments. It's written in Scala, so it uses a few Java virtual machine-based libraries, including BWMirror by Vladimir Jurenka and JBWapi by Jasper Gertz. I'll try to describe how both of these bots work as we go along, but the discussion will focus mostly on PurpleWave since I have more familiarity. These bots interact with StarCraft using the Brood War API. This API lets them observe the game state and send commands back to the game. Part of the challenge of StarCraft is that the players can only observe areas near their buildings and characters, and the API respects that visual limitation. The state-of-the-art bots in this tournament play at a strong amateur level. To put that in perspective, if you wanted to beat them, you'd have to find someone who's spent a great deal of time dedicating themselves to improving their play at StarCraft. They're still a long ways off from beating professionals, as professionals are much better than the amateurs, but they're growing better every year. Because agents send commands directly to StarCraft without using a mouse or keyboard, people often ask whether it's fair to compare bots to humans. For example, the world's best humans play at around 500 actions per minute with mouse and keyboard. But during this game, you'll see bots that are performing up to 20,000 actions per minute. There are a lot of opinions about whether the comparison is fair. I personally don't believe the comparison is fair unless you have an agent controlling a physical keyboard and mouse. But regardless, it's still an interesting comparison. Being able to perform many actions doesn't mean those actions are any more effective. You can trivially write an agent which performs the maximum rate of actions in one evening, but this tournament has, over the past 10 years, demonstrated that the agents have improved greatly over time. So most of the work in StarCraft AI focuses more on making the most intelligent decisions possible, rather than making the human comparison as fair as possible. Most tournaments, including AIIDE, allow bots to save data in between games, enabling them to learn from their previous games against the opponent. Both Locutus and PurpleWave do this, and those adaptations are crucial to avoid being exploited by an opponent who finds a narrow strategy that beats what you're doing. One common approach to learning how to take a strategy against opponents is to treat it as a multi-armed bandit problem, where your goal is to pull the lever of the best strategy to beat your opponent. Common approaches for that include UCB1 and Thompson sampling, but very often, because the opponent is essentially a moving probability distribution, bots will often apply a time decay to the results of previous games, more heavily weighting more recent games to make sure that they're responding to what their opponents are doing currently rather than previously. In this game, PurpleWave and Locutus each scouted each other by sending out one of their worker units, and PurpleWave observed that Locutus was performing a defensive strategy that didn't pose a threat later, although Locutus is secretly building an attack behind it. As a result, PurpleWave reacted by taking this additional resource base earlier. Ordinarily that would be unsafe, but based on PurpleWave's observations of Locutus' strategy, it deemed that it was safe. PurpleWave will also record that Locutus did this defensive opening as well to take into consideration for future games. There are a lot of geographic considerations to go into a game of StarCraft, positional and considering the terrain. For example, this ramp is a narrow entrance into the base. Locutus placed these buildings such that they cover the entrance to the base. Additionally, just placing the maximum number of buildings in the base is a challenge if you want to have the most production possible. So that's where the Brood War Easy Building Library comes in, and now allowing Locutus to tightly pack these buildings, but without impeding the path of the units. Locutus is employing a tactic where it is going to populate this flying ship with combat units and send it around to the back of PurpleWave's base directly to attack PurpleWave's vulnerable workers. This poses a challenge for bots. Locutus is going to send this attack out from the back, while later attacking with its main army from the front. This poses a challenge for the defending bot, which has to decide how to allocate its army units. Does it continue to send bots up front to attack? Does it deal with the main army? How many does it allocate to the attackers in the back? And improperly allocating those army units can result in loss on either front. PurpleWave's units are controlled by individual agents, which are given very rough goals by a planning network that we'll talk about a little later. But those units have freedom in deciding how to execute those goals. These harvesters are still given a general command of gather resources, but they're able to decide on their own, on the moment, I need to be attacking these enemy workers. I need to be bumping into them to try to glitch them out and prevent them from attacking. All of PurpleWave's units operate in this high-level controller, low-level decision-making paradigm. Now, Locutus has moved out with his main army. The Locutus splits its army into different squads, which are then controlled by different behaviors. For example, there was one squad for the shuttle that we saw attacking back here, controlling this shuttle and the zealot that's paradropped in. And it has another squad controlling the main army. As the main army pushes across the map, you'll see that the units are sometimes attacking and sometimes retreating. Deciding when and where to fight in StarCraft is one of the bigger challenges, and something that AIs need to do well in order to play competently. There are a lot of approaches for doing this, but one of the most popular is called combat simulation. You take the units that you have fighting, and every frame or every few frames of the game, run a simulated, simplified version of combat where you take the individual units, replace them with simulacrums representing those units, give them a simplified, inexpensive policy to follow, run through the combat several steps in the future, and then evaluate the outcome at the end and see whether or not you like what happened. Based on that result, you can decide either to engage in the fight or to run away. A lot of problems in bot development come down to a trade-off between being very reactive, deciding what to do in the moment, and having consistent policies that the agent follows. For example, if you reevaluate combat every frame, you may find that slight changes in the initial conditions of the simulation, such as units being slightly more one way or slightly the other, may lead to kind of a butterfly effect and thus high variance in the outcomes of the simulation. So if you run that simulation every frame, make decisions every frame, you may systematically find your bot waffling on its decisions, going into a fight one moment and then pulling out the next. And there are a number of ways to combat that. One approach is applying hysteresis to your combat simulation. One thing PurpleWave does is, if it has a group of units that are fighting, and they decide to fight, preferring to continue fighting for the next few seconds, applying a decaying preference weight to the attack outcome, such that it tends to attack more for those next couple seconds, and then after a few seconds of hysteresis decay, is evaluating the trade-off more fairly. Although that leads to less accurate decisions frame by frame, it systematically produces less indecision and thus stronger overall behavior. There are other approaches for dealing with this. One of those is individual unit simulation. With individual unit simulation, which is used by the bot McRave by Christian McRave and is available in open source format in the library Horizon by the same author, you hold each unit to a specific policy, but measured along the lifespan of one of the units, measure whether outcomes were positive or negative during that unit's combat window. And then each individual unit thus can measure its own profitability in the fight and decide whether or not it wants to fight or flee. This can lead to more fluid behavior, where instead of having a whole army attacking or retreating at once, you have individual units making intelligent decisions. The downside is you may get incoherence, where individual units retreating may essentially lead to incorrect simulations for the other units, which assume those units would fight, and thus you wind up with an army that behaves inconsistently overall. Another approach is to avoid the problem entirely, and this is certainly the least difficult approach to implement, but also the least powerful. But at a strategy level, using strategies that allow you to make a solid guess that at this point in time, I expect that my army is going to be stronger than my opponent, and thus I can move out on the map confidently and attack without a prediction about whether or not I'm going to win, which requires you to be right, but also produces more decisive behavior, and between two evenly matched opponents can result in stronger fight behaviors. Now, as you watch PurpleWave's army retreat from this fight, you may notice that it does it in somewhat of a coherent fashion, that the units are able to retreat without bumping into each other. This is done using threat-aware pathfinding. PurpleWave has a general-purpose A-star pathfinder with a cost function that's parameterized that can accept a variety of different inputs for different purposes. For general navigation around the map, for example, for navigating a unit around, for example, this obstacle in the middle of a path, it uses the basic version of A-star, where distance is cost. But for backing out of fights, PurpleWave can use threat-aware pathfinding, where it uses movement into or out of an enemy unit's range as a cost. This is also similar to a technique called influence mapping. And this allows PurpleWave to retreat its units from the battle and potentially also retreat them towards destinations it wants to get to, like the home base, or maybe, if it has faster units, to retreat out onto the map such that it can later surround the enemy. It's also important when retreating to do so in coherent fashion, such that you're not forming one narrow line of units running away from the enemy, but instead retreating into an arc, such that if you do decide to fight, your army will be well positioned to have the firepower it needs to fight. The way PurpleWave achieves this is by having the units that are closest to the fight, who are most in danger, carve out a path first. PurpleWave then flags the tiles that it would cross during the retreat as more trafficked, more occupied, based on the size of the unit. And then for future units that are retreating in the same frame, increasing the cost of those tiles. This produces more coherent retreats, the units avoid bumping into each other, and it emergently produces concaves, where the units get more firepower than the enemy when they do turn around and decide to fight. An easier technique to implement, which is very common in the StarCraft AI world, in which PurpleWave uses for its flying units, like this observer, is potential fields. This is a purely reactive approach, where instead of planning a path, you model the reasons that a unit might want to move in a direction as forces on the unit. For example, this observer, it's invisible and it can see things, but if it wanders within range of this cannon, it will get shot, or if it wanders too far from the enemy army, and the enemy comes up with its own observer that can see this observer, it can also die. So PurpleWave models the reasons for observer's travel as a force pulling it towards the enemy army, enough that it can see the army, but with a decay such that as it gets further away from its own army, there's a force pulling it back towards its own army, and in an attempt to balance those forces, it hovers in this kind of safe location where it can still see the enemy army. It's less effective at navigating obstacles because it's not planning, it's purely reactive, but it's a very easy to implement and less computationally expensive approach. Part of how PurpleWave actually does its threat-aware pathfinding in a cost-effective fashion is, one, by pre-calculating distances for a variety of important points around the map. So for each of the base locations, like here, or for each of the choke points, it pre-calculates the distance to every other point on the map. And thus it can do an approximate measurement of ground distance across any 2 points of the map very quickly. It's essentially constant time. And then for the distance-based pathfinding, until it gets within a short area and needs to navigate very specific obstacles like a corner of an edge of terrain, it can simply flow downhill along the distance graph and thus do most of its pathfinding very fast. And additionally, for the threat-aware pathfinding, it only pathfinds out far enough to get the unit to safety. So instead of having to path all these units all the way back to their base at home, it just pathfiles about half a screen away. Whatever's needed to get the unit out of trouble. And that's how it's able to rapidly, even on a slowish platform like the JVM, path all these units effectively. Another challenge in StarCraft AI is army allocation, where you send the army. For example, PurpleWave wants to attack this base, but it's also having one of its bases attacked by Locutus. Now, overall, PurpleWave's strategic decision-making, which includes all its spending, things you can see up here, all its army allocation, all its worker allocation, is done with a sort of task network. The overall strategy forms the root of the task network and has a variety of sub-goals. For example, attack the enemy base, defend your bases, build buildings, research technology, gather minerals, things like that. And each of those tasks then may have subtasks which help it achieve that. And one obvious question is, when you have lots of goals that compete for the same resources like units or minerals or space, how do you assign that? And PurpleWave's task network has a strict priority order. The graph is evaluated in pre-order, and the order in which the nodes are visited forms the priority queue. And each item in the queue gets first dibs on any resources it wants. So if the defend your base goal is the top goal, it can recruit all the army units it thinks it needs in order to successfully defend. And there's a system for allocating those units, deciding which are the most appropriate. And then other goals, for example, attack the enemy base, may get second dibs on those units. Another example is gathering. Gathering resources is a very low priority for PurpleWave, so if it needs to construct a building, the build task can pull out the workers it needs to accomplish that. We're going to speed this game up a little bit as it approaches the conclusion. Very tough fight. Locutus managed to have a winning record against every opponent in the tournament, which is a really impressive feat. So this has been one of the games from this year's champion Locutus, and the second place runner-up PurpleWave. If this excites you and you want your bot to be featured next year, you can get started tonight. Check out github.com/bwapi/bwapi and join the community on Discord and Facebook. If you're watching this on YouTube after the AIIDE conference, check out the links below. And even if you're not interested in writing your own StarCraft bot, but you are writing bots for other games, want AI for your own game or for other real-time strategy games, you should stop by and ask questions, check out the source code of these bots, because again, these bots are all open source and many have permissive licenses that allow you to get a jump start on your own development. And that about wraps this game up. Good game. If you're interested in StarCraft AI research, I also encourage you to check out my team's platform, TorchCraft AI. It's an open source machine learning environment for StarCraft Brood War research. It comes with a variety of environments, a variety of neural network agents that you can train, that you can run. It has a lot of different functionality. I encourage you to check it out. Torchcraft.github.io/torchcraftai. Thanks for watching.